Let's get started again. Welcome back. So our next speaker is Ji Qi from Professor Shuiping Ang's group. Shuiping cannot come for his personal reason, so Ji Qi will give this talk on behalf of Professor Shuiping Ang. Ji Qi is a G5 graduate student working on machine learning for batteries. Yeah, so welcome.
Thank you. Yeah. Thank you for the kind introduction. And yeah, my name is Ji Qi, and I'm a fifth-year PhD student at Professor Shuiping's group in UC San Diego. And today I'm going to give this tutorial with title of Machine Learning and High-Throughput Discovery and Design of Next-Generation Electrode and Superionic Materials and their interface for solid-state batteries. So here is the overview of my tutorial today. I will firstly briefly introduce what is machine learning in terms of potentials, and then show you quite a few studies with MLIPs on solid-state batteries. To be specific, room temperature ionic conductivities of solid electrolytes, and also orderings and microstructures of different solid electrolyte materials. And then I will introduce to you our new methodology, direct sampling, for robust and efficient training of machine learning in terms of potentials. And lastly, I will briefly touch the unpublished topic of discovery of new solid-state battery materials with universal machine learning in terms of potentials. So here I give you a short animation of water molecules at room temperature. The motions of water molecules are actually derived from the Newton's law of motion, where the forces, interatomic forces, are derived from the potential energy surface. Traditionally, there are two types of simulations and with two types of potential energy surface defined. First is with rigid functional forms. We do classical molecular dynamics. This is a highly scalable method that can be applied to millions of atoms to microsecond scale simulation, but its transferability and accuracy is limited by the rigid functional forms. While for the ab initio molecular dynamics, we use approximations like density functional theory to solve the Schrödinger equation and get the potential energy surface information. And this method is highly transferable and accurate for the whole periodic table, but its scalability is very poor. It can only be applied to, say, 100 picosecond scale simulation within 1,000 atoms. And here comes the machine learning in terms of potentials. So basically, it has two enabling parts. The first is a sophisticated local environment descriptor that transforms the geometric information surrounding each atom to the local environment fingerprints. And the second component is a machine learning algorithm to correlate those local environment fingerprints to the potential energy surface, which is, the ground truth potential energy surface, which is obtained from ab initio simulations. So these machine learning in terms of potentials, in short MLIPs, they have been verified to have very good accuracy for a lot of systems that is similar to their training structures. And today I'm actually going to show you what have been done with machine learning in terms of potentials to study solid-state electrolytes in the last 4 years. So let's start with the introduction for my studies. So here I show you some previous results on two well-known solid electrolytes, the Li7P3S11 glass ceramic material, and also the lithium-3 yttrium chlorine 6 solid electrolyte. For these two materials, we can see a common feature from a common gap between the AMD result and the experimental result is that the AMD simulated room temperature ionic conductivity is a lot higher than the experimental measured results. That's the case for LPS. And also, it's even more severe in the LYC case, where the AMD overestimate the room temperature ionic conductivity for more than 10 times. Also, the activation energy is underestimated by the AMD results. So if we have a detailed look at those AMD results and the experimental result, we can see the experimental results are usually measured at room temperature range below 400 Kelvin and to around 300 Kelvin. While for our simulation results by AMD, it's conducted at about 500 Kelvin. And a constant activation energy is assumed and extrapolated down to room temperature to get the ionic conductivity. So we trace back the inaccuracy of AMD results to two problems or two limitations in AMD works. The first is the high computational cost. So because of the high computational cost, the AMD can only be applied to study fast diffusion, which is at high temperature region. And we know that this won't work for materials like lithium lanthanum titanium oxide, where we for sure have the non-homogeneous behavior, which is a increase in the activation energy at low temperature region. So if we still assume a constant activation energy at high and low temperature region, then the extrapolation down to room temperature will for sure overestimate the room temperature ionic conductivity, like the AMD works does. Okay, and second limitation is that for AMD, still related to the cost, we usually use the typical PBE functional and just use some very simple gamma point, K point density to study the system. So this, the accuracy is also biased or compromised by the functional we use in the simulation. So to tackle these two challenges, we use this workflow to train machine learning internal potentials for these three Superionic conductor systems: lithium lanthanum titanium oxide, LYC, and LiPS. So in this workflow, we actually first do DFT relaxation to get the ground state structure for these three lithium Superionic conductors. And here we consider two DFT functionals, the PBE functional and also the OPB888 functional, which actually incorporates the van der Waals interactions to the functional forms. So after we obtain the relaxed structure, we perform AMD simulations at a temperature range from 300 Kelvin to 1200 Kelvin, and then apply different strain level to those AMD simulations to obtain the training structures for our machine learning internal potentials. And for each lithium Superionic conductor system, we have 1800 training structures. So the next step is that we do DFT static calculation to get accurate training energy and forces for those structures obtained from ab initio molecular dynamics. And the last step is use those training structures and training energy and forces to feed moment tensor potentials, which is again machine learning internal potential that describe the potential energy by the summation of atomic energies, and atomic energies are defined to correlate the local moment descriptors, where here the moment basis functions that incorporates radial and angular interactions into their basis functions. So here I want to stress that by this workflow, for the three systems, we have two functionals considered, the PBE functional and OPTB888 functional. And again, we use two functionals to generate training structures and two functionals to generate the training energy and the forces. Then we have three training sets. The functional labeled in front of the comma is the functional we use to generate the structures, while the functional we use after the comma is the one we use to generate the training energy and forces. So here I'll give you just the 6 plots of parity plot for the test arrow for energy and forces by our moment tensor potentials compared to the ground truth DFT results. So you can see that for the 3 cases of different MTP labeled with their training structure and training data, training energy and forces, the test arrows are all comparable. Especially if we look at the middle 2 figures, we can see that even though we use PBE to generate the training structures and OPTB8 to generate the training energy and forces, we still get comparable test arrows for energy and forces. So we continue the verification by comparing the lattice parameter relaxed with the experimental result. On the left plot, we can see that for LTO, those two functionals perform comparably for in terms of the density compared with experimental result. While for LYC and LiPS, we can see that PBE underestimates the experimental density, while optivated has a more accurate result in terms of the matching with experimental density. And if we look at the right plot, we will see that the MTP exactly reproduces the result of DFT. And the exact functional it reproduces is the functional after the comma, which is the one used to generate energy and forces. So this actually tells us that we can use a relative cheap functional to generate the training structures, while we use more expensive and more accurate functional to generate training energy and forces. So this is also the same case verified by the equation of states for those three models, that three systems, that the moment tensor potential trained with the PB or trained with the functional used to generate the energy and forces reproduce the result for that specific functional. And then we use the moment tensor potentials to simulate ionic conductivity in those three lithium superionic conductors. Here I give you the Arrhenius plot simulated by those 6 MTP potentials. And you can see that, interestingly, we observe a transition of activation energy at around 400 to 500 Kelvin by the potentials trained with energy and forces generated by optivated functional. And here I summarize the result of experiment, AMD, and moment tensor potentials in this table. You can see that for LLTO, there is, the two moment tensor potentials trained with PBE or optivated energy and forces actually have comparable results, and they both match with experimental results. And also the both ionic conductivity and activation energy are reproducing the experimental results. While for LYC and LPS system, we need the optivated functional to generate the energy and forces in order for our ionic conductivity to match with the experimental results. And we also further studied what happens before and after the transition temperature at around 400 to 500 Kelvin. So we observe exactly at 500 Kelvin, compared to the 300 Kelvin trajectory for lithium diffusion, there is an expansion of the diffusion trajectory dimensionality. So this is correlated to the decrease of activation energy at high temperature. So we further used this, as a short conclusion, machine learning potentials can be used to bridge the gap between AMD simulated room temperature ionic conductivity and the ionic conductivity measured by experiments. So we continue to apply this to study sodium diffusion in this sodium yttrium zirconium chloride system, which is actually a structure where we dope zirconium to the sodium yttrium chloride structure, and we obtain high ionic conductivity with this NYCC75 composition. So in this case, again, the moment tensor potential trained with AMD structures and PBE functional energy and forces match with the experimental results. While if you look at the AMD result, if we extrapolate down from high temperature region, then we will have overestimated ionic conductivity and also underestimated activation energy. And again, we also observe non-Arrhenius behavior at around 500 to 550 Kelvin. And this time, we trace back to the mechanism to the rotation of chlorine surrounding the yttrium and zirconium octahedrals. As you can see that in the same time frame, if the temperature is above 500 Kelvin, then the chlorine is actively rotating. It's actually like a pedal wheel effect during the dynamics of the chlorine surrounding the yttrium and zirconium cations. So for this NYCC system, there are actually a lot of things that we don't understand by then. For example, we have 2 types of sodium environment in the NYCC system. So there are 2. So for each unit cell, there are 2 prismatic sodium sites, while there's 1 octahedral sodium sites. And according to our collaborators' result in NMR, we see that the bone marrow sample actually has a higher amount of octahedral sodium on the octahedral side, while the slow-cooled sample has more sodium on the prismatic side. So this echoes with our DFT result that with more sodium on the octahedral side, we actually have a higher energy of the stable structure, which it's a reasonable result that the ball miling tends to help the system to go to a higher energy states. And beyond the sodium local environment, there's another type of cation ordering that is actually even harder to measure in experiment, which is the short-range order between yttrium and zirconium cations, because these two cations are really close to each other and they have very similar atomic weights. So in experiment, it's very hard to detect this short-range order. And in this case, we use the SRO parameter to define different short-range orders for the yttrium zirconium local environment. So you can see that on the left one, here we have 3 layers of zirconium and 1 layer of yttrium. So this is like a layered transition metal ordering, while in the subfigure B, we have 1 layer of mixed yttrium and zirconium cations and another layer of pure zirconium. So we name this as a mixed transition metal ordering. So we have 2 types of yttrium zirconium ordering and a few types of sodium environment. So you can imagine if we want to simulate these 2 different cation orderings in NYZC, if we use AMD to generate the training structures, it will be quite expensive. So this time we actually use the active learning workflow of moment tensor potential, which is a method that detects extrapolation on the fly. So to be specific, we perform molecular dynamics on the simulation scenarios of interest, and we use the extrapolation grade to evaluate if the moment tensor potential has extrapolation on each of the MD snapshots. And if there is extrapolation detected, we will perform DFT static calculations to get accurate energy and forces for that structure and augment the training set with that new data. Well, if no extrapolation is detected, then we'll continue the molecular dynamic simulation. So with this method, you can imagine we don't need to perform DFT in order to evaluate the test error for each MD snapshots, and that enables us to evaluate a lot more snapshots during the test process. And more importantly, let's get rid of the AMD in the generation step of training structures. So with this workflow, we perform active learning on actually a lot of cases where to be exact, it's 4 temperatures for the 8 NYZC75 structures spanning 2 yttrium zirconium short-range order and 4 different values of sodium octahedral site occupancies. So in those 8 structure cases, we perform active learning again at 4 temperatures from 300 to 1200 Kelvin. And you can see that after 32 iterations, all the molecular dynamic simulation for 100 picosecond can complete without any newly emerged snapshots that is detected to have extrapolation behavior. So in other words, the MTP can perform reliable simulation for 100 picosecond for all those temperature and structures after 32 active learning iterations. So with this active learning moment tensor potential, we again study the sodium diffusion. And here is the Arrhenius plot we got. You can see that a very interesting trend is discovered that for the layer transition metal structures, which is in circle labels, they have very similar ionic activities at room temperature, also activation energy. While for the mixed transition metal structure, you can see that those 4 samples are also having comparable ionic activities, but they are much higher than the ionic activity of the layered transition metal structures. So this also tells us that the initial sodium octahedral site occupancy doesn't matter to the ionic activity. And we further investigate the reason for this. So by looking at the 400 Kelvin evolution of sodium octahedral site occupancy, we can see that although we start from different values, different initial values for the sodium octahedral site occupancies, they actually equilibrate very fast within 20 picosecond to a value around 30%. So this tells the reason actually why, even though we start from different sodium hydroxide occupancy, they actually converge to equilibrium value when they have the same yttrium zirconium layer transition metal site ordering. And remember that the AMR result tells us that the ball mill sample actually has a high sodium concentration on octahedral site, and it has a high ionic activity. So we further look at the equilibration of the sodium octahedral site occupancy. You can see that here, for the triangle labels, they are constantly having a higher sodium octahedral site occupancy. So this actually tells us that the four the four samples with mixed transition metal site ordering for the yttrium zirconium, they actually have a constantly higher converged sodium octahedral site occupancy. So that explains the fundamental reason for the experimental results to see why there is a higher sodium octahedral site occupancy in the ball mill sample with high ionic activity. And actually, the more fundamental ordering is the yttrium zirconium pattern ordering other than the sodium octahedral site occupancies. So then we also have another study on the structural disorderings in lithium yttrium chloride. The reason why we want to study this is that in experiment we see a very, very interesting result that by ball milling by ball milling the sample, experimental results shows that it obtains low crystallinity in the ball mill sample. You can see that there's peak broadening in the XRD results. And by this ball milling, they actually obtained a high ionic activity, around 1 order of magnitude higher than the high crystalline LYC. So we are interested to study this amorphization effect on the ionic activity for LYC material. And again, we use active learning to sample training structures for our moment tensor potential to study the amorphous phase of LYC. Okay, so you can see again, this is a similar workflow that we apply the active learning to 5 different temperatures from 300 Kelvin up to 1800 Kelvin, which is, at least 800 Kelvin above the melting temperature of LYC. So with this model, we will be able to do some interesting workflow like this melt and quench procedure that we can melt the structures. You can see that there is a melting at around 1100 Kelvin, and then we quench down the sample with 3 different quenching rates to maintain the liquid-like structure. So from the RDF, you can see that at 1500 Kelvin, there is no long-range orderings, and the 3 different quench samples have comparable RDF at this long-range region, and also they equilibrate at similar volumes and densities. So with this, with this active learning workflow, we are actually quite quite confident to generate this kind of amorphous structures with this melt and quench procedure. And then we further studied Arrhenius behavior, actually simulated the ionic activity at from 300 Kelvin to 1000 Kelvin. And so similarly, we see that the crystalline phase comparable to a previous result is that we see a transition at around 500 Kelvin, and the activation energy is like 0.57 eV at low temperature region, actually room temperature region. While for the amorphous structures, here we studied the sample with 2 different quenching rates, and we can see that they actually have very comparable ionic activities, which is comparably higher, more than 1 order of magnitude higher than the ionic activity of the crystalline phase. So if we look at the XRD of the computed structure, you can see that the 3 quench samples with different quenching rate, they again have the amorphous liquid-like disordering in their XRD plots. That's definitely you cannot see any crystallinity in those amorphous structures. But this is still different with the low crystalline phase in the LYC experimental result. So from our result, it tells that if we can fully amorphize the LYC, then we will be able to get even higher ionic conductivity than the current value of around 0.5 millisiemens per centimeter. And I mean, we are also actively working on trying to build some partial amorphous structure that mimic the structure in the experiment. Okay. So let me move on to the study of macrostructures, green boundaries of oxide perovskite electrolytes. So here again, I want to mention this famous lithium superconductor conductor, LTO. It actually has a very good ionic conductivity that discovered 30 years ago to be around 1 millisiemens per centimeter at room temperature. But this material is, it has a very high green boundary resistance. So this blocks is a real usage as a solid electrolyte material. But in exactly the same perovskite structure, but there's different composition, lithium, strontium, titanium, zirconium, tantalum, zirconium oxide. So this structure, it's the same perovskite structure as LTO, but for this material, the green boundary resistance is actually very small. And this is why we're interested to look at the green boundary of this structure and to see why the green boundary resistance is not high in this material compared with LTO, which has the same structure. So again, we use active learning workflow to fit moment tensor potentials to study both bulk and green boundary of this LSTZ 0.75 perovskite structure. So in this workflow, in the first step, we generate an initial training set by performing MD simulations and static calculations. And with the initial training set, we start active learning in 2 stages. The first stage we do MD, and second stage we do MCMD to green boundary models. And you can see after, say, around 35 iterations, there is no new extrapolative structures emerged in all those simulation scenarios up to, say, 2100 Kelvin, and which is already 500 Kelvin above the experimental calcination temperature. Then we also validate that our structure, our moment tensor potential have comparable training error and test errors for energy and forces. And actually, more importantly, you can see there is a convergence of the predicted green boundary energy by our moment tensor potential to the DFT ground truth. Okay, this is just example for one orientation of green boundary, but we actually have 4 different orientations in our test set, and you can see they have good matching with the DFT results. And for green boundary orientations out of the training set, our moment tensor potential also has reasonable accuracy comparable to the orientations included in the training data. So with this moment tensor potential, we first study the ordering in the bulk LSTZ 0.75 structures. So this ordering is defined as this function to actually describe the ASAT alternate stacking. So you can see that at 0 Kelvin, the most stable structure actually has lithium and lanthanum stacking in terms of for one layer there's strontium-rich layer, while for the other layer the ASAT has more lithium on it. And this is when all the strontium is in one layer, the S parameter is equal to 0.778, which is the alternate stacking, while for S equal to 0, it represents a disordered ASAT. So we see that at higher temperature, we perform MCMD and the equilibrium structure will be having a disordered ASAT ordering. So this, by visualizing this, the evolution of the ASAT ordering parameter, you can have a better understanding that at lower temperatures, the S parameter stay constant at around 0.778, representing the ASAT alternate stacking, while for higher temperatures, the disordering ASAT is promoted. And we also study activation energy and ionic quantities for those 4 samples equilibrated from MCMD simulations. So we can see that disordered structures with S equal to 0 have a smaller activation energy at room temperature range. Also, it has a higher ionic activity. So this actually is a good verification to our MTP model that this trend is also known in the LTO case, where disordered lithiums and lithium and lanthanum ordering on A set is promoting the ionic activities. So then we move on to study the green boundaries. We have 5 green boundaries with low sigma and high sigma values, and we performed MCMD simulation to allow atom swap at 1573 Kelvin, which is the experimental calcination temperature. You can see that, interestingly, for example, here we clearly see that there's a slight increase in the lithium concentration at a green boundary region, while for strontium, there is a decrease in the green boundary composition. Green boundary concentration. So this actually tells that there's no lithium depletion at green boundary, which was actually one major reason why LTO has a high green boundary resistance. And instead of lithium depletion, we actually have more strontium vacancies at the green boundary region. And by looking at the diffusivity at green boundary and compare with the bulk region, we will see that the ionic diffusivity in the green boundary region is just 2 to 3 times lower than in the bulk region for the 3 green boundary orientations that we studied. And actually, if we check out the diffusion along the green boundary and across the green boundary, they actually have comparable values. So that tells the reason why the green boundary of lithium, LSTZ has low green boundary resistance. So we continue, to study even more complex systems like this high entropy lithium strontium, tantalum, niobium, zirconium tin system. And this LSTNZS system, we have comparable results to the previous system in terms of the local composition in green boundary and regional diffusivity for green boundary. Actually, in experiment, they also got no improvement in terms of those ionic connectivities, things like that. But here I want to highlight that in this workflow, we apply same active learning workflow. But if we look at the active learning iterations, this time actually takes us a lot of time, actually more than 100 active learning iterations to get a reasonable moment tensor potential to study this system, because the system has a really complex chemical composition, and which also increases the complexity of the moment tensor potential. So you can see that after 50 active learning iterations, actually we still cannot complete even 0.1% of the 100 picosecond simulation, which is actually below 100 steps of MD simulation in our cases. So to tackle this challenge, we actually try to use some method developed by our group. So this universal potential is called Materials three-body graph network model, and this is developed by Dr. Chi Chen in 2022 in our group. And you see this model is material graph network model that incorporates both two-body interaction and three-body interaction into the local element descriptors, and they use the graph convolution to transfer the information between bonds and nodes. And then again, just similar to other MLIPs, it calculates the atomic energy and sum them to describe the potential energy of structures. So for this model, it's trained with more than 100,000 structures and data in the material project, spanning 89 elements. So with this universal potential, it's actually verified to reproduce DFT results in terms of, say, structural realization to a very good accuracy, I won't introduce too much of it in this tutorial, but you are welcome to refer to this reference to check it out. But the main message in this slide I want to show is that now we may have the possibility to not only get rid of AMD in our structure generation step, but also we might be able to eliminate active learning iterations in the structure generation step for MLIPs. So here is what I did. So you can see that we compare 3 sets of structures for the titanium hydrogen system. The titanium hydrogen system is a challenging system even for AMD because hydrogen is diffusing very fast. So we usually use a very small time step of say 0.5 femtosecond in AMD simulations. So here we have 3 sets of structures. One is AMD structure obtained at 1000 Kelvin for 3 compositions. The other is moment tensor potential active learning structures that is 2063 structures collected at the same condition as those M3D&MD structures, which is actually this structure space. So you can see by visualizing the PCA feature space of M3GNet structure feature, we actually see that both the MTP active learning structure and M3GNet-MD structure covers the AMD sampled regions. And also they actually sample comparable regions in terms of the just the 2-dimensional PCA space. So it tells us that M3GNet-MD structures mostly cover those features sampled by the 2 methods. And I come up with this dimensionality reduced encoded clusters with stratified sampling method, in short, direct sampling, to try to create a subset that have robust coverage in terms of the features that we sample in whatever structure generation scheme, like AMD or M3GNet molecular dynamics. So especially we are doing actually featureization, dimensionality reduction, and then clustering to cluster structures into different regions in the feature space, and then we do stratified sampling from each clusters so that both common and uncommon features can be selected by this workflow without like oversampling the common structures and undersampling the uncommon structures. So I will discuss more about it on December 1st. So you're welcome to join this presentation where I will better explain these workflows. But the result is that by this direct sampling workflow, we are able to definitely outperform the manual sampling with fixed intervals to cover a more diverse feature space. You can see both for one trajectory and for all the 274 MD trajectory, our coverage by direct sampling is better than the manual sampling to cover the feature space in terms of the visualization. And we also trained the moment tensor potential with 2 different training sets. One is the direct sample structure set. The other is the active learning set. And we use 2 test sets. One is from AMD. The other is from the MTP MD that is performed to a 1 nanosecond long time scale to get the end structure and spanning a range of temperature. So you can see that the moment tensor potential trained with active learning has comparable force error with our direct sampled MTP, with our MTP trained with direct sampling dataset. While for the energy, I would say they still have comparable values. While for our direct sampling dataset, it has a slightly higher test error. But this is, I would say, more or less acceptable considering the different size of our training data. And more importantly, we use the 2 moment tensor potentials trained with active learning set and direct set to study the hydrogen diffusion in different polymorph structures of titanium. So you can see that here we studied FCC titanium, BCC titanium, and HCP titanium. We can see that there is a clear trend that agreed by both MTP model that the diffusion in the BCC titanium is the fastest, while in the FCC one it's the lowest. And this actually, the ionic conductivity, the diffusivities and also activation energies match very well with the experimental reports. And in terms of the comparison with AMD results, both MTP models have a good agreement with AMD. So, and we further test the stability of our moment tensor potential trained with the Dirac set. So here I compare actually two active learning schemes starting from different initial structure sets. The first case is the from scratch, which is starting from, say, 90 structures, which are ground state structure for titanium hydrogen structures. And the other case, which is case 2, is the starting from the Dirac data set. And you can see that, you can see that for starting from scratch, it takes 28 active learning iterations to get to a stable MTP that can complete all the 274 MD scenarios. While for starting from Dirac sample dataset, at 300 Kelvin and 1000 Kelvin, there isn't any active learning needed to get this reliable simulation for those 91 crystalline structures for titanium hydrogen. While for 300 Kelvin, we still need a few iterations to complete those MD simulations reliably, but this iteration, it's largely decreased to just 5 iterations. And this result is actually not surprising because, like reported by the MTP developers, if you start from if you start from the on-the-fly active learning with a well-designed pre-learning data set, then you will need a much smaller amount of DFT calculations in order to get a stable MTP. So the message here is that direct sampling coupled with any structure sample generation procedure like the M3G9 molecular dynamics will be able to get a very good, robust, very good initial training set for the MIP training for our solid-state battery or any any interest systems. So, and lastly, I will touch the topic of discovery of solid-state electrolytes. Here I want to show you a few studies before 2020. Those workflows that's high throughput to discover solid electrolyte materials from, say, SSB database or material project. And I see there are some general limitations in those workflows. For example, in this one, applied by our group, we always use something like topological analysis, this kind of indirect properties to infer diffusivity instead of directly study the room temperature on the conductivity. And also, we have relatively small candidate pool, say material project, which are all known materials instead of new materials. And we tend to focus on the ionic conductivity, while as Dr. Wang has already mentioned, there are multiple objectives when we try to discover this kind of solid electrolyte materials. Other than ionic conductivity, we also need to care about chemical stability and diffusivity. So those are unpublished results, and we are still actively working on this, is to try to use the M3G9 universal potential to do high throughput discovery for this solid electrolyte materials or solid state battery materials. So here are some benchmark results studying the oxidation voltage and reduction voltage for sodium containing materials in the material project. You can see that actually M3G9 has a very low error in terms of those activation, in terms of those electrochemical windows. Also for the reaction energy with different cathode materials, it also has a very low error around just 3 MeV per atom compared with the DFT. Also, it can give us some reasonable estimation to distinguish good ionic conductors from poor ionic conductors. So here I want to draw a conclusion to my tutorial today that MIP's bridges gap between the ionic conductivity measured by experiment and simulated by DFT, and They also enable study into different orderings and microstructures in solid-state battery materials. And direct sampling is developed to accelerate the training of reliable MIPs. And lastly, universal MIPs like M3GNet will enable, it's already enabling discovery of solid-state battery materials from very large candidate pool. Yeah, thank you for your attention.